Good morning, everybody. Sorry I can't be there right now. I am at a meeting right now with the other second and third year teachers upstairs. It should not last too long. I'll be back probably by around 9:20, 9:30, somewhere around there. So we'll do a lab when I get back. It'll be kind of cool. We'll build molecules. But for now, let's do some other stuff. Um, so yesterday, we took a lot of notes. It was crazy. I threw a lot of information at you and it was confusing. And I thought about it and I thought we should maybe step back for a second. So there's a worksheet that the substitute teacher will give to you. Um, and I'd like to tell you how to go through it. So if you want to pause right now, get the worksheets, and then we'll take just a little bit of notes and I'll tell you how to do it. All right. Do everybody have the worksheet with you? Okay, great. You'll notice on one side there is something about ionic bonds, and there's a data table. On the other side, there's something about covalent bonds. So check it out. Here's page one, ionic bonds, and then page two is covalent bonds with some practice. So what I'd like you guys to do is right now, you can fill out just the first and second rows in each table. This row, those two rows, and these two rows. So you can do this quickly. I don't think it'll be a big problem for you. Please pause the machine as long as you guys need, maybe 4 minutes, I would think. All right, 1, 2, 3, go. Okay, welcome back. Let me tell you how to do this. So in this spot, we have sodium, NaF there has 11 protons. As if it's neutral, it'll have 11 electrons. And in its valence shell, it's in that first column. We know 1s2, 2s2, 2s6, 3s1 has one valence electron out there. All right, chlorine, on the other hand, has 17 protons. If it's neutral, it will have 17 electrons. And it has a total of 7 valence electrons. We know that because it's 7 over. You can also recognize that it's 3s2, 3p5. All right, so you've got that done on this side. Now let's go down and see what we have to do with this. It says for each of the following ionic bonds, write the symbols for each element, draw a Lewis dot structure for the valence shell, draw an arrow or more if needed to show the transfer of electrons, and write the charges on the ions and the resulting chemical formula. Then I'm also going to ask you to write the name of the formula, compound. Mm, mm. All right, so let's get started. All right, so I blew this thing up so we can see a little better. First things first, let's draw the symbols for each element. We've got where's my so sodium is Na, chlorine is Cl. And this is draw the Lewis dot structure for the valence shell, just the valence shells. Sodium has 1 electron in its outside shell, so we get those. Chlorine has 7, so you can go 1, 2, 3, 4, 5, 6, 7. Now here it says, on the other side you can rearrange them. I drew this one facing sodium because I know they're going to bond. All right, now it says draw an arrow or more if needed to show the transfer of electrons to the new element. So I'm going to change colors here real quick. And we'll see that this sodium and chlorine has a much higher electronegativity. We know that because it's on the right side of the table. It's got a higher Zeph. So it's going to pull in electrons more strongly than sodium will. Sodium will drop that electron over there. What that does is it gets rid of that electron for sodium. So now the question becomes, write the charges on the ions. So if sodium lost an electron, what's its charge? It becomes +1. If chlorine lost an electron, it becomes -1. So now what you have is a +1 sodium, -1 chlorine, and they become NaCl. Sodium now is empty. That's good. Chlorine is full. Everybody's happy with everything. Now, the last part, what do we call this stuff? Metals keeps its name. Sodium fluor, but because it's a negative ion at the end, the anion goes to hide. This because it's an anion right off the periodic table. Okay, you can pause this and work on it yourself if you'd like to. I'd like you to take a couple minutes and work on the next one, magnesium and iodine. You can pause it if you like, or you can just keep listening. I think you should pause it and try it for a second. Okay, give it a shot. Come on. Okay, I'm assuming you worked long and hard on that. You want to verify your work. So let's take a look. Um, okay, so we write the symbol magnesium plus iodine. Yeah, I'm drawing that in a weird place. All right, now let's do the dots. Magnesium is two families over, so we know it has two dots. Iodine is in that seventh family, just like chlorine. So 1, 2, 3, 4, 5, 6, and I'm going to go 7. All right, so iodine has higher electronegativity. It's on the right side. It's a non-metal. What they do is take electrons. Magnesium is metal. They lose electrons at low electronegativity. So what you see happening here is, and then magnesium. Magnesium loses its valence electron there, um, and iodine gains one. So what happens to the charges now? Iodine becomes -1, and now it's got the 8 that it needs. So iodine is cool. Iodine's happy and stable. What happens to magnesium now? It lost 1 electron. Now it has a charge of +1. Is it happy? Does it have everything it needs? Remember, what is everything on the periodic table doing? They're trying to gain or lose electrons to have a stable octet, empty or full. Magnesium still has 1 electron it needs to get rid of. Where can it possibly go? Can't fit on that iodine. Aha, but what if we had another iodine? 1, 2, 5, 6, 7. This electron then can go. It's lost over here. All right, this magnesium, I'm sorry, this iodine ion is now -1. Magnesium is now 2 plus because it lost 2 electrons. Magnesium's happy, iodine's happy, iodine's happy. Our formula, MgI2. And this is called magnesium chloride. All right, let's take a break from this for a second. Let's go to the back page. Dealing with covalence. Wait a minute, how can you tell if something is covalent or not? Well, it depends on where they are on the periodic table. Remember, covalent bonds are those that have similar electronegativities, so they're going to be close to each other on the table. Specifically, if there are two nonmetals, that's probably what you're going to get, although there are other weird things. Anyhow, carbon, how many protons? 6. How many electrons? 6. The valence electrons, count from the left, 1, 2, 3, 4. How many electrons do you need if you wanted to fill the outer shell? Carbon can use another 4. All right, hydrogen, 1 proton, 1 electron if it's neutral. How many valence electrons? 1. How many electrons does hydrogen need to fill that outer shell? Well, remember, hydrogen's small, it's unique. It can only hold up to 2, so it just needs 1 more. All right, let's go down here. All right, so now we're going to do something kind of similar. Write the symbols for each element. Go back to black here. Hydrogen, 1 dot. Another hydrogen, 1 dot. I'm putting them between each other because I know they're going to interact somehow. Dot structures, rearrange the electrons to pair them up. That's what we did. We rearranged them a little bit. And then draw circles to show the electrons in pairs that are being shared. So we'll take a nice happy little bond. Circle those. And what you got yourself there is a chemical bond, a shared pair of electrons. We've talked about that. That's what a bond is. It's a shared pair. So what's the structure of this thing? The next step, I believe, is H, and then just a dash to another H. Remember, we talked a little bit about that. That dash just means a shared pair of electrons. All right, what's the formula? H2. Just 2 H's bonded together. That's hydrogen. That's just how it appears. What's the name of this stuff? Nothing fancy. It's called hydrogen. Wait, what? Isn't hydrogen just H? No, that's a hydrogen atom. They do not appear like that in real life because they have one out electron in their outer shell. Hydrogen is always either bonded to something else or bonded to itself in pairs. It's one of those diatomic elements. All right, let's go do something a little bit more complex, perhaps more interesting. Okay, let's do hydrogen and oxygen over here. You have seen hydrogen plus, or I'm sorry, it's just got one electron on the outside shell. We know that. We know oxygen has 1, 2, 3, 4, 5, 6 in its outside shell. This one's trying to get filled. This one's trying to get filled, but we're doing it covalently because there's similar electronegativities. So they say, hey, why don't we do that? Why don't I use a different color? Why don't we share this guy here? And we got ourselves a chemical bond. Hydrogen now has 1, 2 electrons at its disposal. It considers itself full. Oxygen now has 1, 2, 3, 4, 5, 6, 7. Wait a minute, that's not going to do it. What else can oxygen do to get itself stable? It can find another hydrogen. And they can form another bond. Doing this. This hydrogen feels good. It's got 2. This hydrogen's good. This oxygen now has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its valence shell. So what is the formula of this guy? I think you know it. You recognize it. H2O. What's the molecule shape? It would be like this. That's right now. We'll learn more about this when we get back to class. Those dots are those unshared pairs. H is on either side. What do we call this stuff? I know you want to call it water, and that's okay. Everybody will know what you're talking about. However, the technical name is dihydrogen monoxide. And ask me about a very silly story about that name in a town in California that almost banned water from their town because they didn't do their high school chemistry. All right, you guys, take a shot at finishing up the front of this sheet. Take a shot at finishing up the back of this sheet. Use this video as much as you need to get you through it. I think you guys are quite capable. Good luck and enjoy. I'll see you in a while.